Good morning, everyone. I'm Ruiqi from the University of Hong Kong. And the topic of my today's presentation is the turbulent transport mechanism in the Roughness Sublayers over idealized urban area. And the content of my today's presentation is separated into the four parts. And first, I will introduce the background and knowledge gap of our research. And the atmospheric surface layer is consists of the initial sublayer and the roughness sublayer over the buildings and trees on the surface ground. And but the most exciting studies they are more focused on the smooth wall or arrays of the identical roughness elements. There is a lack of the systematic investigation behind the RSL RSL dynamics over the urban areas using the drag coefficient, and they also so that the objectives of our research is that using the drag coefficient as a metric to quantify the roughness as well as to study the associated transport mechanism rather than only regard the drag coefficient as aerodynamic parameters influenced by the urban morphology. And this is the layout of our cube type configuration in our wind tunnel. And uh, in addition, the height of the cube type increased by mounted the double, triple, and quadruple Lego block layer to increase the drag coefficient. And we calculate the drag coefficient using the friction velocity and the free stream velocity, and this is shown the drag coefficient of different roughness element configuration. And first, I will talk about the three boundary layer parameters as a function of drag coefficient. And first, it's the TPL thickness delta. And we can see that from this figure, the delta is generally increased with the increasing drag coefficient. It is because that the delta is developed by the roughness element. And the second is the zero plane displacement d, and we cannot say it is not notable relationship between the d and the drag coefficient, so that it is not necessary to use the d to represent the aerodynamic resistance. And the third parameter is the roughness line Z0. And the Z0 increases with the increasing drag coefficient, so that it is reasonable to use the Z0 as an indicator to represent the aerodynamic resistance. And and it is the mean wind speed profile of different roughness elements. Uh, and first, we can say that the conventional log law view represents the ISL mean wind speed profile, but in the RSL, it has a discrepancy with the conventional log law, so that we can see that the RSL mean wind speed are more uniform than the RSL counterparts. And we focus on the RSL parts. The mean wave speed have shifted downward with the increasing drag coefficient. And then we induce the indicator, the exuberance eta. It is defined to compare different roughness elements, compare the transport efficiency over different roughness elements. And the closer the eta to zero, the more efficient transport. And from this figure, we can see that The transport efficiency is starting from the ISL bottom and arrives its maximum in the ISL uh, and then decreases with the height increases. And from the different drag coefficient, we can say that with the drag coefficient increases, the transport efficiency uh, is increases. And we say that uh, the case C4D, C4T, and C4Q, we can say that the building height variability plays an important role in the transport efficiency. Uh, in particular, close to the urban canopy. And then we use the then we use the two angle and or use the causal analysis to investigate the turbulence characteristic. And then firstly, I calculate the two angle. The two angle is obtained by linear regression of the most energetic events Q2 and Q4. We got the theta, and the theta equal to 45 degree. It means that the turbulence is isotropic, and we can say that with the drag coefficient increases, the two angle is also increases. So it represents that the vertical uh, the vertical transport becomes more energetic with the increasing drag coefficient. And in the out layer, it seems the difference is small, so that's and it's converged to the TBL top, so that it means that the ISL and the out layer, the flow in the ISL and the out layer is not influenced more by the urban canopy. And next, I want to talk about the spectral analysis. And this figure is the pre-multiplied spectra of the U prime prime and W prime prime. And the first, we will focus on the energy intensity. With the drag coefficient increases, we can see that the energy intensity is also increases. And another one is the vertical grade is the vertical gradient of the vertical gradient over the wavelengths. So that we can say that with the drag coefficient increases, the gradient is decreases. So that means that the smoother the surface is, the faster the rate at which the dominant eddy size increases with increasing height in the ISL, and the lower the energy it delivers. And it is the shape contour of the energy spectrum of the C4 cases. And an interesting finding is that we found that in the cold spectra, it's in the short wavelength region. It occurs a secondary peak, but we cannot find in the streamwise direction and vertical direction. So that it means there is not local TKE maximum in the same area. And we also compare the different drag coefficient, the conversion of the different drag coefficient, and we found that the drag coefficient has the secondary peak has some connection with the drag coefficient. With the drag coefficient decreases, the energy is the secondary peak, the energy is increased. And the more uniform RSL is attributed to the high to the large to the large energy carrying scale together with the small but more correlated small scale. And it is about the isotrophic, and we do induce a parameter that the isotrophic parameter. The parameters tends to be one that mean that the structure is more isotrophic, and we can see that the even the RSLs, even the small scale in the RSL, it becomes more anisotrophic, but the scale with the isotrophic scale increases with the height increases. And another is we focus about the large wavelength region that with the drag coefficient increases the RSL the isotrophic tendency is increases, so that RSL turbulence tends to be more anisotrophic when it's approaching to the rough surface. And from this figure, we focused on the energy intensity that we proposed. A hypothesis is that as the drag coefficient increases, the TKE production decreases, but the entrainment increases, and we will verify in this figure. We calculate the TKE production budget and the TKE and the turbulent TKE flux, and the positive of the turbulent TKE flux presents the entrainment. The negative is the entrainment. And with the drag coefficient, increases, the TKE production decreases, and with the drag coefficient increases, the entrainment is increases, so that the rougher the surface, the lower the production, but the higher the entrainment. And this is the conclusion of this research, that the project analysis and two-angle demonstrate the transport. And we found the interesting finding in our research is we found a secondary peak in the co-spectrum, and also we found the entrainment and the production, the relationship of the entrainment and production with the drag coefficient. Thanks for your attention.
Questions? Yeah. Okay. Since you are analyzing the turbulent kinetic energy budget, so I have a question about how do you calculate the fraction velocity, the U star, or you mentioned the U tau, the first question. The second question is, do you think the increase of the production of the TKE budget is coming from shear layer or coming from the high velocity gradient?
The first question is about the friction velocity. And the friction velocity is obtained by the maximum the momentum flux using it. Yeah, and the second question is it's about the production, and we think that the more efficient transport is because the it's not contributed by the production, but it's entering the energy from the out layer and through the ICL and down to the RCL. So that, yeah.
More questions?
Yeah. This is perhaps a little bit philosophical, but why do you frame the question in the context of drag coefficient? Well, on one hand, the drag coefficient seems to be. Why do you formulate the question in the context of drag coefficient instead of other parameters, like say the morphological parameters, which is more typical in the literature?
Yeah, because from the previous studies, we have that the rougher the surface, the more transport. But we want to know why the rougher surface of more transport. So we use the drag coefficient as an indicator or the metric to solve this problem.
I need to think a little bit more.
Yeah, thank you.
Okay, I think we have to move on because we are